Hey physicists, let's take a look at this problem, which will help highlight the differences between gravity mass, let's see, inertial mass, and then rotational inertia mass. Okay. So I have this rod here. Okay, it's attached to a pin, and it's free to rotate around the pin. We'll assume that this is an overhead view, and it's on some type of frictionless surface. The mass of the beam is 5 kilograms. We'll assume it's uniform in its cross-section along there. It's initially at rest, and as noted, it can rotate around this point right here. A little drawing there. Mass of this, we have a piece of clay. Clay is often used. We could call it a bullet or a dart or something, but clay will deform, but it's moving at 25 meters per second. At a position 3 meters from the beam, and notice that's at right angles there. And at impact, it sticks to the beam, and then the clay and beam will rotate together. So we have a couple of questions. First is, what's the angular velocity, omega, immediately after the impact? B. And what's the tangential velocity of the end of the rod out here? So with that velocity, B. And C. If the rod has 3 Newton meters of friction between this post here and the rod, how far would it rotate till it stopped? If this was a let's see, I guess we'll call it a translational problem, we could see this pretty easily as we end up having an inelastic or perfectly inelastic collision that our momentum before is going to equal our momentum afterward. And we just find out what velocity is needed to keep that momentum the same. And if we had some type of friction as it slid, we would find out what that velocity was, what the acceleration was, and we could figure out how long this would take till, well, how far it would go till it stopped. And really, it's not going to be any difference when we do it here. We're just going to throw in some rotational components as well. Okay. Hey, so I've stated a couple of important ideas here, that our initial angular momentum is equal to our final angular momentum, and that'll be just before to just after the impact. How can we figure out angular momentum? There's 2 ways we could do that. We could look at the radius. I'm going to make that a vector. Okay, the radius cross product momentum. Of course, our momentum is m times v. Okay, and a cross product. These are at 90 degrees, so we won't even have to worry about it much there. Or I could say my angular momentum, analogous to translational motion, is I, our moment of inertia, times our angular velocity. Okay. And so let's go and we'll start looking at these values. Hey, so if I take a look at my initial momentum, or angular momentum, and the only thing that will have initial angular momentum will be our blob of clay, because our rod is at rest, it won't have any angular momentum. So I could just use this formula, my radius 3 meters times 0.3 kilograms times 25 meters per second, and I get 22.5 kilogram meters squared per second. I could have also figured that out using kind of the other formula, where I say, hey, I omega initial, and we take a look at that. Our I, in this case, would be mass times the radius. We're going to assume that this blob of clay is small enough that it's considered a point mass. And our omega, we could kind of try to figure that out, but we could also say that our omega is equal to our velocity over our radius, and it might be a bit easier to figure out that way. You can do it for yourself. You can take my word for it that I omega, this way we're going to get the same value as if we did it as we did here, where we do radius times our momentum. Our final angular momentum will be the moment of inertia of our rod and blob together, times that final angular velocity, and that's the value that we're actually looking for. We know that numerically it's going to be equal to our initial angular momentum. Let's see if we can figure out what that final moment of inertia is. It's going to be the moment of inertia of the rod, I guess I'll call it that, I mean, rod or beam. I'm going to use B. I've been using that up here. Okay, plus the moment of inertia of the cable. Okay. Hey, so taking a look at the shape of this, we know that our moment of inertia for our beam is going to be 1/3 times the mass of the beam times the length of the beam squared. And for our clay, we know it's just a point mass, so we're going to have our mass of the clay times the radius from that pivot point. We can put in some numbers to come up with our values here. Okay, so our moment of the inertia for the beam, hope I mentioned this before. For the beam, remember, for a long cylinder rod about one end, the moment of inertia is 1/3 ml squared. If this had been a disc rather than just a beam, we would have used 1/2 mr squared. If it had been a a rod about its center, we would have used 1/12 mBl. Right, just those various shapes. All right. If it's been a hoop, then we know that we'd end up just using whatever the mr squared. Okay, so I take 1/3 5 times 4 squared. I get about, let's see, 26.7 plus 3.3 times 3 squared. I get another 2.7. Altogether, we have our moment of inertia for this thing after the clay sticks to it is 29.4 kilogram meters squared. Okay, so why am I looking for the moment of inertia? Just getting back to a discussion from last class. We're looking at how much inertia or resistance to motion this thing has. Okay, how much resistance to twisting motion? It has 22.4 kilogram meters squared of resistingness. If it was a linear movement, then we'd only worry about its mass. But this one, we're rotating it, so we're worried about how it's that mass is distributed as well. The further out the mass is from our chosen rotation point, the more difficult it is to get it to rotate. Okay, so I know my final momentum, angular momentum, is equal to my initial angular momentum. So all our final angular momentum will be 22.5 kilogram meters squared per second. Hey, we know that this value here is going to be our final moment of inertia, so we know our final angular velocity will be our angular momentum divided by our moment of inertia. So omega is going to be 0.765 in our units. Notice everything cancels but the per seconds, and so it's going to be radians per second. Final angular velocity 0.765 radians per second. Hey, B, we're looking at the tangential velocity at the end of the rod. So right here, how fast is that going? Really in meters per second, because we're looking at a tangential velocity. This one's going to be pretty straightforward. Hey, our velocity is really just going to be omega r, and that's going to be true of most of our rotational to translational conversions. If we just take the angular value times the radius, will give our linear value. So what's that going to be? You're going to have 0.765 radians per second times our radius 4 meters. We're looking at the outside edge. Yeah, put that in the calculator to find out. That works out to about 3.06 meters per second. Pretty straightforward there. For section C, we wanted to see how far this was going to rotate after the blob of clay had stuck to it. I've added a few things here, just redrew it because our initial drawing went off the edge of the page. So we now have our rod and blob of clay rotating, I guess I'll call that counterclockwise or right-hand rule out of the paper at 0.76 radians per second. We have a torque or frictional torque, so that's going to oppose motion. We have a torque at this pin of 3 Newton meters. Let's take a look at how far it would rotate. In a translational problem, if I had an initial velocity and a final velocity, okay, and I was looking for, let's see, displacement, and I could somehow figure out my acceleration, then it's pretty clear I would use our favorite kinematic equation, a v final squared equals v initial squared plus 2a delta x to figure out my displacement. Hey, no difference here. We can go ahead and use our favorite kinematic equation, but we're going to put in our rotational variables in there and go ahead and solve this. Okay, so I've added those. Our initial angular velocity is 0.76 radians per second. Our final, remember we want to know how far this is going to rotate, so till it's stopped, our final angular velocity is going to be 0. Delta theta is what we're looking for, and our angular acceleration alpha. With the information here, I've got a torque and a moment of inertia. Of course, that'd be analogous to our linear world of force over mass. Okay, let's go put in some numbers here. I'm going to just give myself a little bit of room here. Okay, so my alpha is going to be equal to my 3 Newton meters. That's my torque. And my moment of inertia, I fortunately still have it up here, 29.4 kilogram meters squared. You know, to save yourself a little time on the AP test, putting these units are only needed at the beginning and the end. I tend to carry them through the calculation. But you can see it just takes a little bit of time and doesn't add to your understanding. Hey, so if I divide those, I get an angular acceleration of 0.102 radians per second squared. I'm going to call what is it, my counterclockwise direction is positive. The torque is opposing that, so our acceleration will be negative. Hey, so I've rewritten our kinematic equation for use with angular variables, and I'll go ahead and put those in. So I have a omega final squared is going to be equal to omega initial squared plus 2 alpha delta theta, and that's of course what we're looking for is delta theta. So let's put our values in. Our final, it's going to be 0. That's going to be easy. It's going to be equal to our 0.765 radians per second squared plus 2 times our alpha. I'm going to put that minus 0.102 radians per second squared. I am just drawn to always putting in units. Sorry about that. I just feel a need to do that. Times delta theta. Let's go and isolate things here. Hey, so just a little bit of arithmetic here. I'm going to square 0.765, square that, I get 0.585. Move it over to the other side, I get negative 0.585 divided by 2 times this negative 0.102. I do the math here, and I get 2.86 radians, about half a turn. So it ended up rotating all the way over to about there or so. Hey, so just a couple of notes on this problem. Hey, if we had had an angle other than 90 degrees, you know, we had, which I'm going to call it phi for right now, just not to mix it up. Okay. If I had some angle phi and still my blob had the same mass and was going the same velocity, hit further out here because of the angle, this would end up being exactly the same problem we had before, because if we look at that cross product where our angular momentum is r cross p, hopefully you'll see that, hey, anywhere along this line of action here, I would end up having a, I guess we can call it a, kind of like our moment arm of 3 meters from our pivot point up to the, let's say our line of action. Okay, if the rod was down over this way and hit this, our answer for the rotation would end up being exactly the same. Hey, something you might notice, in those who play baseball, softball, golf might know this. Notice this. Hey, if I were to have the blob of clay hit further out here, and let's say it wasn't pinned, this whole thing would tend to kind of rotate counterclockwise. If I had that same blob of clay hit a little closer in this way, it would tend to rotate the other direction. Okay, so you can see there's a position somewhere along here that if I end up hitting it, the amount of rotation I would get would end up being, or it would rotate around this point here. Whether it was pinned or not, it would still rotate about that point. For athletes, particularly baseball players, softball batters, golfers, would know that position, when it hits at just the right spot, would be known as the sweet spot. You don't get that sting in your hands. Why is that? Because the rotational and translational motions end up meeting so that the bat or whatever would kind of rotate the same way, and you wouldn't end up having to apply any force to it to keep it in your hands. If you wanted to model this a little bit differently, and we want to have a little more time to do that, you can think of our slender rod out here, or our rod, and we end up striking it at some point. We're just going to rotate this all now. We rotate it, we strike it at just the right place, and would rotate about this this point here. This is starting to look a little bit like a baseball bat. You notice how on a baseball bat it gets thicker toward the end. We have a greater mass out toward the end, and then we have a skinny handle, and our hands are here. All right, just kind of a little bit of application of what we're doing here. Hopefully you saw here was we had inertial momentum axially, or actually linearly when we had our blob of clay. We picked a rotation point, so that had an angular momentum, and then we had to preserve that for both before and after our impact. Maybe some other extensions to this problem could be, we would see how much kinetic energy the blob had before impact. We would see the amount of rotational kinetic energy it had after the impact. Where would that energy have gone? You know, into deforming the blob of clay. Hey, after a period of time, we know that this rotates only let's see, 2.8 radians. So it had some kinetic energy just after impact and ended up stopping. Where did that go? Went into friction in this pivot point here. If you went into engineering, you wanted to say, hey, how much is that going to heat up? If you knew the specific heat and the amount of energy that was in there, we could get an idea of how much the temperature of that would increase due to the friction. All right, so just some extensions on what we're learning here.